Then we're going to go out of order today because the next topic is really kind of technical and it's going to take at least 2 days, if not 3, and it's sort of awkward to do it with the test right in the middle of all that. So we're going to do something that is less technical and jump to numerical integration. And we're really, I won't say like not necessarily close in terms of time, but in terms of material, we're really close to finishing this integration technique stuff. We're missing partial fraction decomposition, which is a specialized tool for rational functions. And we're missing trigonometric substitution, which is a specialized tool for certain sort of square roots. It's a little hard to summarize, but the important word there was specialized. We're not going to learn any magic bullet technique that will allow us to deal with any integral. And the end result of this is going to be a huge number of integrals that we just can't take by hand. Here's one of them. It's very easy to write down. It's not super complicated, but none of our techniques work here. It's not U substitution, even though we've got this composition, because for U substitution, we need a 2x, or at least we need an x. If we were missing the 2, that wouldn't be so bad. And it's not integration by parts, it's not a product. Putting a 1 there like we did with the natural log doesn't get us anything. Specifically, if we try this trick, Lyot suggests this, and then we'd say, cool, well, I don't know what the integral is. That's what I'm trying to figure out. So that doesn't work. It doesn't have the square roots that suggest inverse trig. It doesn't have the square roots that suggest trig substitution. I know we haven't talked about that yet. It's not a rational fraction, so it's not partial fraction decomposition. It's just this integral that we can't take, even though, from our point of view at this point in our career, none of these functions are complicated. And I didn't have to work to create this. And I guess I was forgetting, it's not a power of the sine and the cosine, so we can't use the tricks from that section. And it's really easy to write down functions where we cannot find antiderivatives. And the question then becomes, well, just because we can't find these antiderivatives doesn't mean we never will need to integrate these. So if you run across that in the wild, I want to say that the sine and cosine of x squared show up in optics applications. then what do you do with it? And the answer is, well, we can't find it exactly using the fundamental theorem of calculus, but we can numerically approximate it. And the way I'm framing this, numerical approximation comes across as kind of a last resort, but I'd say in a lot of applications, it's actually going to be your sort of go-to thing. Like, we can use numerical approximation techniques. For example, if we're given a function in the form of a table, like we're monitoring somebody's blood pressure throughout the night or something. And so we have data like every 15 minutes or every hour, and we have, well, blood pressure is a bad example because it's not just a number, say heart rate. So we have a table of data. And we are interested in integrating this, and the fundamental theorem doesn't work because the fundamental theorem requires you to have a function whose antiderivative you can find. We can't do it when we just have a table of data. But we'll see there's a very standard way to approximate integrals when we have tables of data. So these approximation techniques are useful when you're just stuck with an integral you can't take, but they're also useful in other situations. And you shouldn't be afraid of approximation. Like I'm going to talk to you as if you were all taking this for engineering or something, even though I know you're really trying to be teachers, most of you. Because I mean, I think the feeling that, you know, maybe the textbook gives, at least by sticking this at the very end, is that this is like a failure state. You can't get the integral, but at least you can numerically approximate it. And I mean, what I'd say to that is, okay, well, suppose we have something like the integral from 0 to 0.7 of the cosine of x dx. This is an antiderivative we can take. But I mean, this isn't much of a way to write your answer. The sign of 0 is fine. The sign of 0 is 0. But what's the sign of 0.7? Well, it isn't anything. I mean, it's an infinite decimal. It's irrational. It's non-repeating. So we go to our calculator, or as the case may be, I went to Wolfram Alpha, but it looks like maybe Firefox crashed between then and now. So let's go back to Wolfram Alpha. And we type in the sign of 0.7, and we say, well, it's about 0.644218. if I'm remembering that correctly. So that's an approximation, and we could keep more decimals if we wanted to, but no matter how many decimals we keep, this answer is an approximation. So you look at this, where everything works perfectly. We take the antiderivative, but we still wind up with an approximation, and then we look at this, where the antiderivative doesn't work, but we can get an approximation. I mean, we're winding up with an approximation either way. So, in like applications, you should not be shy about using numerical approximation techniques. Honestly, even, I mean, if an integral is enough of a pain, I wouldn't hesitate to just approximate it, even if you could find the answer exactly. So with that, sort of trying to puff is wrong, because I mean, trying to build this material up appropriately, not as something you do when everything else fails, but as a valid technique of approaching integration. There are three sort of standard methods for approximating integrals. And these, you would not do any of these by hand in real world settings, of course. There are implementations of these in Python and all of the standard algebra packages like Mathematica. But we can present these, and we can tell you what's happening. And these techniques are pretty much the techniques we have. Like sometimes in a class we'll present, here are some things we can do, but if you look at like the programs, they're doing all kinds of complicated things behind the scenes that aren't really what we teach you. That's not the case here. I mean, there's a limit to how well we can do this, and the techniques we're going to present are that limit. And all of these techniques, are based on the same principle that we're trying to find an area under a curve, or a weighted area under a curve, as the case may be, and we can approximate that to too big an interval, but we can approximate that by cutting the interval up and approximating it on each of these pieces. And we've already seen that using rectangles, and we'll see variations of it today and Wednesday, but we'll start with rectangles. So as a reminder of how this approximation worked, we cut the interval up. So we look at a little sub-interval, like we look at this sub-interval here, and we select a point inside the interval, x sub I star, and we'll call the width of the interval delta x sub I. And we draw a line up from that point. The height of that line is f of x sub I star. And we use that to create a rectangle, and the rectangle has that as its area. And then we take all of those approximations and we add them up, and that's a Riemann sum. And the limit of the Riemann sum is an integral. And, our first observation is going to be that we might not be able to take an integral, but we can always find a Riemann sum. A Riemann sum is just a bunch of multiplications and additions. So our first numerical approximation technique is Riemann sums. And we call this a rule. It's not a rule. I'm not quite sure where that terminology comes from, but the midpoint rule is really just the observation that you see here. We selected a point that was kind of close to the edge of this interval. The midpoint rule is just the observation that if you select the points right in the middle of these intervals, you'll usually get a better approximation than if you select points at the edges. So we cut the interval we're looking for. I am recording this. We cut the interval we're looking for into pieces. In terms of the midpoint rule, the pieces don't have to be equal size, but usually they will be. So we get a bunch of pieces that look like this. Again, you can usually just assume the pieces are the same size and not worry about keeping track of each of their individual lengths, but that's the width of the piece right there. The midpoint mathematically speaking is the average. So x sub I plus 1 plus x sub I over 2. And then you get the width of, the height of the interval by evaluating f at that midpoint. And you multiply it by the width to get the area of one of these rectangles, and you add them all up, and there's the approximation. And again, the midpoint rule is tedious to do by hand, but its great advantage is that you can always use it. I mean, assuming that you know what the function is, you can always use the midpoint rule to do a numerical approximation. And I say it's tedious to do by hand, but who's doing this by hand? A computer can use the midpoint rule in 1,000th of a second. And let's assume that we've got the same width. So there's some common delta x. We don't need to worry about these delta x X is plural, we'll just cut the interval up into equal parts. That assumption makes it slightly easier to talk about. So let's say we use n rectangles. Where cutting up into intervals, so n is 1, 2, 3, 4, 5 here. So delta x is going to be b minus a over n. Here's a, here's b. So b minus a is the length of the interval, and we're cutting it into n equal pieces. So b minus a over n. And you know, as n goes to infinity, this approximation gets better and better. This approximation gets closer and closer to the integral you're looking for. And yeah, and I can make this statement because assuming that these are all the same width stops me from doing anything goofy. Without that assumption, we could keep increasing the number of intervals while just keeping this big interval there, and then you'd always have error because of that. So making them all be the same width is ensuring we're not doing anything goofy like that. And yeah, so this is the midpoint rule. It's a little tedious to do by hand. These are all a little tedious to do by hand, but let's look at an integral we could take not using the midpoint rule. And let's find the exact answer here. And then let's use the midpoint rule and let's see what we get. So as far as finding the exact answer, 1/3 x cubed plus 1/2 x squared minus x from 0 to 2, 8/3 plus, so 4 over 2 is 2 minus 2. Okay. So even with this, sort of going back to what I said earlier, if you wanted this as a decimal, it's what, 2.6 repeating? So if you entered it, if you were like working on a spreadsheet and entering data into a spreadsheet, well, you can't tell Excel 2.6 repeating, so you'd have to round it, so you'd wind up with error anyway. Going back to what I was saying about not stressing about that, because it's always gonna be there. Let me quickly, by the way, here, Have you used anyone in this room Wolfram Alpha before? So it's I use it as a mathematical tool. It can do other stuff as well, but the idea of Wolfram Alpha is that it's like a MATLAB or Mathematica replacement that uses a common language input. So if you wanted to take an integral in MATLAB, you need to look stuff up and you need to make sure your commas and your semicolons and everything are in the right place. Whereas here, integral from 0 to 2 of x squared plus x minus 1. And we get this. And you know, it doesn't rely on us asking the question in any specific way. If you've ever used, probably this is unlikely, but if you've ever used LaTeX, here's how I would typeset that to create it on a test. You see, it can look at that and see what's going on. Anyway, so 2.67, and this is also giving us 2.667. Again, that's wrong. That's rounding error. But it's the kind of wrong that you can't really get around. Let's use 6 rectangles and the midpoint rule. And let's see if we get close to 2.667. So really, the midpoint rule is slightly tedious just because of all of the setup. I mean, we need to find all of the midpoints to use the midpoint rule. So here A is 0 and B is 2. And we're assuming that we've got this common delta x. We'll always just assume we have rectangles of the same size. There's another rule that will work better if we don't. So 2 minus 0 over 6 is 1/3. So the slightly annoying thing about the midpoint rule is that these numbers I'm putting on the board are not the numbers we need. These are the intervals. The numbers we need are the midpoints of the intervals. So that's going to be 1/6. It's again, the midpoints, you can think of them formally as an average. So the average of 0 and 1/3 is a 1/6. The average of 1/3 and 2/3 is 3/6. The nice thing is that the distances between the midpoints are fixed. So from 1/6 to 3/6, this distance is 2/6, and all of the distances are 2/6. So we don't have to mess around with averages anymore. We can just count up by 2/6, and these are going to be our midpoints. And another nice thing with the midpoint rule, using the assumption that delta x is fixed. You know, the first term is going to be f of 1/6 times delta x. The next term is going to be f of 3/6 times delta x, and so on. So we can pull delta x out. 1/3 f of 1/6 plus f of 3/6 plus f of 5/6 plus f. Oh, gross. Now, sorry, forget you heard that, but there's our numerical approximation, and it then does become a little tedious, and I wonder what the best way of doing this is. I mean, now we need all of these function values. So we take each of these numbers, we square it, we add the original value, we subtract 1. I wonder if, so Wolfram alpha sometimes does exactly what I want it to do, and sometimes I have to fight it. But like if f of x equals x squared plus x minus 1, find f of 1/6. It can do that just fine. So let's see if you can also find. Let's see, what's that delta x? That delta x is 1/3. So 1/3 times f of 1/6 plus f of, or counting up by 2, right? Let me also share this. F of 2/6 plus f of 5/6 plus f of 7/6 plus f of 9/6 plus f of 11/6. Let's see, feel like something went a little wrong here.
Is that second one supposed to be f of 3/6?
It is supposed to be f of 3/6. Thanks for catching that. Okay, so we get 2.6, which is not the best approximation. I was honestly hoping for a little more, but I mean, it's accurate up to the first decimal place. And of course, because we're doing this by hand, we sort of had to, where'd our work go here? Because we're doing this by hand, we were sort of limited in the number of, let's try that again. the number of rectangles we could use. Let's see if f of x equals this, use the midpoint rule. N equals 10. Approximate. I'm in uncharted water here. I have no idea if Wolfram Alpha is going to like this or not. It will integrate it, but it won't conveniently use the midpoint rule specifically. Oh, well. I mean, I was just even with that. I mean, I was just making the observation. I don't know if anyone's like, what happened to all my slides? Slides have all disappeared. Well, anyway, I was like, I don't know if any of you have programmed in Python or whatever, but it's very straightforward to like tell a computer I want to do that, but instead of using 5 rectangles, I want to use 5,000 rectangles. And that error will very quickly disappear. Continue to be. So what? It's 9:40. We have 10 minutes. The test is tomorrow. Probably better do the trapezoidal rule on Wednesday and Simpson's rule on Thursday and let out a little early today.